Okay, we're going to talk about subsidence. Okay. And clearly subsidence is part of the spectrum of slope stability questions, but it's one that is of particular interest in certain geologic settings. Okay. Now, if we talk about the lowering of the land, and more specifically how that happens and why it's a problem, there are both, I'll finish when they're finished back in the back. You through? Ready? Okay. There are natural processes, dissolution, and these result in a type of topography we call karst terrain. And so that's one of our geomorphic clues that this is a problem. Compaction of unconsolidated sediment. This is a natural process that goes on, results in subsidence. And tectonic subsidence. And that tectonic subsidence can be either, let's just take an example, the sinking of the ground associated with an earthquake in a subduction zone, or it could be the lowering of the ground due to salt withdrawal. So in the case of the Gulf of Mexico, in this area, we have a lot of salt. It's relatively mobile, and so as it moves, it tends to rise in diapirs, and then in the in-between areas, it tends to subside in bowls. And so we have a lot of up and down movement associated with tectonics and salt. In fact, we often talk about salt tectonics as opposed to the movement of plates and faults. Now, the other type of subsidence, or the other processes, are human-induced or anthropogenic subsidence. And one of the things that happens is we're basically removing stuff from underground and it collapses. That's kind of like a man-made dissolution. Oxidation of organic rich soil. We'll talk about that in a second, but that is a process that is associated usually with draining of swamps and a removal of subsurface fluids and resulting subsidence there. And there's a case where we are compacting clay-rich sediments causing lowering of the ground. That's of particular interest here because that is the kind of subsidence that has affected the Houston-Galveston area rather severely. And in most textbooks, that's kind of our claim to fame, is that we are a textbook example of subsidence due to groundwater withdrawal. Okay. Karst topography has a variety of geomorphic clues. Sinkholes are the most obvious, but there's a variety of things that indicate extensive dissolution of soluble material. And I should add that although the most common bedrock that is dissolvable is limestone, we also can dissolve evaporites like halite or gypsum. And in some cases, we have what's sometimes called a pseudo-karst. We have collapse features associated with volcanic rocks. And that's an unusual case, but important locally, because when particularly basaltic lava flows, they'll often flow and then cool at the surface, but continue to flow in a channel at depth. And that results in what we call lava tubes. And so these are literally long tubes like caves with a relatively thin surface from the cooled lava. And so as these break down, that is another form of karst or pseudo-karst. Okay? Sinkholes are pretty obvious, and we'll see a lot of those. You look around in areas like Florida, they come in all sizes. And as we'll see in just a couple of minutes, there are different types of sinkholes that occur in different geologic settings. Okay? And of course, what the sinkhole really is just the surface exposure of a cave at depth. So when we think about caves, this is simply the surface extension of that dissolution. So this is a case where the sinkhole is above. In the extreme case of karstification or forming karst material, you get these rather unusual forms of like karst towers in China that are kind of the end member of modifications, beginning with the flat surface and some holes. Now we basically have all holes with few flat surfaces. Okay. So these are all geomorphic indicators of dissolution at depth. Now, where does it occur? Well, it actually occurs over a wide area. This is a geologic map showing areas of karst. And let me point out that in this particular example, the karst that is in the panhandle is actually due to the dissolution of gypsum, an evaporite. Okay? The karst that we see in the central Texas in blue, well, that's the Edwards Plateau. In fact, let's look at a somewhat different one. Here we've got a map that shows karst from evaporite rocks, that's these way in here, and karst from carbonate rocks, okay, like the Edwards Plateau. Now, I'm going to come back to notice these areas right here, including near Houston. That's karst from evaporite rocks. What do you suppose that really is? It's a salt dome, yeah. Mm-hmm. So we got these salt domes coming up. They literally have come to the surface, and we have dissolution that's causing the subsidence. We'll actually see an example of that. Okay. These are the areas that are under eventually have surface solution. Here's the Gulf of Mexico. You realize that the entire Texas coast and all of Louisiana and much of Mississippi are underlain by evaporites, but the surface solution is restricted to just a few areas. That's not the case with subsidence. In a broader sense, in the areas that are underlain by salt here are areas where we are experiencing regional subsidence. So one of our issues in terms of things like coastal flooding is to try to be able to differentiate how much of it's due to eustatic or worldwide sea level rise due to things like global warming, and how much is it due to lowering of the land by maybe tectonic subsidence. Okay. Just another picture of the same thing. These are the areas that are risk, and from subsidence in general, and you see that it's not just karst. All of this area here has the potential for subsidence. Basically all of Florida. And then, of course, areas where you have carbonate rocks exposed. Okay, so we've got a lot of area that's underlain by evaporated rocks, as well as evidence of surface dissolution. Okay, in Texas, just going back, the Edwards Plateau is the one that we are probably most familiar with. This is where the caves are. This is where our sinkholes are. This is where Cretaceous limestone has been uplifted, dissolved, and pitted. Notice also, though, there's some stripes. And what these stripes are carbonate rocks that have been tilted and then eroded. And so we're looking at little strike exposures of the carbonates as part of a larger zone of faults and tilted rocks. Notice we don't have any down here. Now they're actually from, there are some due to salt domes, but for the most part we only have siliciclastic or shales and sandstones cropping out here. In terms of Texas history, the days of the carbonates died about 60 million years ago. And so since then, we basically have been looking at sandstones and shales. Okay. If we go to areas like Florida, we see that there's a lot of urbanization. I mean, basically people have built around these sinkholes, and it's, you know, these are great. They are nice circular lakes that you can build around and have your boat docks, and so they have a lot of attraction. But we really need to pay attention to how they form, because they are, in fact, not a relic feature, but they continue to form today. So we're going to look at three types of sinkholes, and here I'm mainly talking about carbonate sinkholes, cover subsidence, cover collapse, and solution. Okay, so let's see what those are. A cover subsidence. Okay, here's a case where, first of all, we have some covered material. Okay, water is sinking through that cover, and we're getting a little dissolution. Okay, and so it might look something like this. Here is the cover, whatever that might be. And water's coming down, it's beginning to dissolve in here. A little more dissolutions occurring, and notice we're beginning to get a lowering of the cover. Basically, the cover is subsiding, okay, until finally we've got the cover that has gradually dropped into this dissolved space below. Okay, that is usually not aggravated by human activity. More importantly, it doesn't occur very suddenly. It's not a major hazard. Cover collapse are more serious problems. They occur very quickly. These are deep-sided holes that just drop literally overnight. And so if we look at that, here we got the cover again. Here's a hole, and that hole is getting bigger and bigger. Literally, that hole is a cave, basically, until finally the whole thing collapses. And the cover, it just goes down, and these things can go down hundreds of feet and be rather large. We'll see pictures of that in a moment. The third is a solution sinkhole, and basically it means there's no cover, but we're just, for some reason, focusing on dissolution in one place, and so you gradually have a lowland develop. And again, these are not particularly hazardous, but it'd be like the cover subsidence without the cover. So these are the three kinds of sinkholes. Oops, let's go this way. Okay. If you go to Florida, Florida is the home of the sinkholes. And the headlines in Florida are pretty spectacular as they talk about California sinking into the sea. Well, here it's the sinkholes are going to rip Florida in half. We have a sinkhole plague in some areas. And so let's look at where these active sinkholes are. And it does seem that they tend to cluster. There are, even though the entire state is covered with limestone, clearly the conditions for active sinkholes are more restrictive. Okay, and so we see some large areas in here. And then if we take a little area here, we see some large areas here. So what we want to do is try to figure out why there and not someplace else. Well, this geologic map is really a sinkhole map. It's kind of almost like a sinkhole inventory. Now, better a sinkhole hazard now. They're not inventorying the individual sinkhole. That would be a sinkhole inventory. But rather they're defining areas that have different types of sinkholes based on the geology, the amount of cover, etc. So in yellow, where you notice there's not many sinkholes, you have either bare or thinly covered limestone. So if you have a sinkhole, it's solution sinkhole. Then areas that are covered. Well, you've got 30 to 200 feet. And then more than 200. Now within 30 to 200, you've got two different kinds. You've got material that is permeable sand, and there you have cover subsidence typically, and you have material that's impermeable clay. There you have cover collapse. And so the permeability of the overlying material is not just having cover, but the permeability of the cover will determine, are we going to have cover subsidence or cover collapse? When you think about permeability, it kind of makes sense that if you had permeable cover, then water sinks down, infiltrates, and then is dissolving the material below. Okay, and the whole thing just gradually subsides. If it's impermeable, then you get a different groundwater situation where you're dissolving the material, but you're keeping this cap until it fails. Okay. Now, once it's too thick, you don't have too many sinkholes, but when they do, they're really big because literally a couple of 100 feet of cover is collapsing all at once. Okay. So let's look at, this is just explaining that in a little more detail. And this is just the potential for possibility for sinkholes. And again, it has to do with the type of material and the thickness of the overlying material. And again, just as we had with landslides, low, medium, and high, this is kind of low, medium, and high. This doesn't really tell us the risk, but it just says that it's kind of relative danger. It's almost into hazards. Okay, and so this is what Florida uses to try to require certain types of insurance and certain types of geological studies depending on the area. Okay, that's good. Yes. This here? I can't hear you. Oh, here? Oh, here? That's Lake Okefenokee. Okay. Yeah.
Can you go back one more as well?
Mm-hmm. Here?
No, yeah, you're there. So, because the second map that you showed shows kind of like different results.
Oh, well, a little different scale, but see these here? That's this in here. And then this little area in here is this little area in here.
And on the next one, when you look at it, I guess...
Now, this is the same map. I just literally enlarged.
I guess on the next stuff that you look at. Yeah, on that one.
Oh, this? Okay, again, I got to figure out where the area is.
So it's the same area.
Yeah, see this right here? That's this right here. And it kind of comes in like this. This right here is this right here.
And it's showing on the left one that's the highest.
Oh,
one is showing that it's
well, no, see, this is a confined aquifer, but this here is real thick. So the hazard is relatively low in the sense that, or the frequency, because they don't happen much. When it happens, it's pretty big, but confined aquifer and or more than 100 feet of overburden. So that's relatively low. Here, we've got moderate overburden overlain by cavernous limestone with a potential for catastrophic steep collapses. Okay, so thickness of overburden isn't the only factor. You can have none and you have no problem. As it gets thicker, depends on whether or not it's clay or sand. And then if it gets real thick, it's relatively rare. Okay? Okay. So let's see about how we create sinkhole. Kind of like how do we create a landslide? Well, there are natural and anthropogenic triggering events. Heavy rain, a drought followed by heavy rain. One of the things that tends to destabilize these potential sinkholes is rapid rise and fall of the water table. Okay, and in some cases even animal activity. Okay, more typically heavy pumping of groundwater. When we're drilling for other things, if we evacuate or overload over a void, a broken water line, ponding of water, pile driving with vibrations. These are all construction activities that can create an event that causes the sinkhole to collapse. Okay, so let's see what we might have. Here's the hydrostatic pressure from the aquifer. It's a confined aquifer. Here we have pressure from standing water with a pond. Let's see, we've got vibration due to a new construction. We've got a well pumping water up and down. There's a variety of things that we might do to create this hole, okay? Or rather to call it to collapse. So here is the situation in Florida. Here is a sinkhole. Notice the roads are around it. This is a very nice sinkhole in Avon Park. This is one that was quite a surprise. Okay, this has been around a long time, and you've built around it. Everybody's quite happy to have it. This one happened overnight. Okay, you can see where there were buildings. It's over 100 meters in diameter. Just think of a football field collapsing. Okay, with over a couple of $1 million of damage. Okay, coming across into the road through this building, etc. So we can have massive sinkholes occurring in a moment. This one, interestingly enough, this is actually the same sinkhole, just from the ground. You see the camper and with the truck and the buildings, etc. Okay, as realtors say, it's location, location, location. Literally, in some cases, it's right under a house. Here, it's right under a series of apartments near Disneyland. Okay, and you can see the expanding concentric cracks, not unlike you would see on a rotational slide, except that it's concentric. Okay, and in this one, literally somebody was killed when the sinkhole collapsed under the bedroom. So these things are immediate, and clearly, as is shown here, they can occur where people live. Usually, there's warning. Now, the warning is your house is beginning to fall down, but fatalities are relatively rare, but loss of property is huge. Okay, and literally, it starts something like this. Here's a little hole. That's usually not a good sign, and it gets bigger and bigger quite quickly. Okay. Now, in this one, this thing is 30 stories, about 100 meters deep. It's just fell through took out a whole 3-story building. It's 60 feet wide, 30 meters deep. Okay. Clearly, it had been forming over a long period of time, but what precipitated it was 3 feet of rain that was a tropical storm that came in. Okay. So these things this would be your deep-seated, sudden collapse sinkhole. Okay, so these are extreme events, and of course the point here is that they happen today. These aren't simply things that have happened in the past. What do you do about it? Well, actually, one of the things that increasingly people are doing in Florida is, one, buying sinkhole insurance, like you do in California for earthquake insurance, like you do in Houston for hurricane insurance. But the other thing is, you do exploratory drilling, and literally you fill the incipient cavities with concrete. So unless it's too big a hole, you can deal with this preemptively. So this is a case where, at least in many cases, you can actually prevent the hazard from occurring. Okay. As you might imagine, there's a lot of lawsuits that involve people not telling there's a problem, or engineers missing a problem, etc. Okay. So this is of ongoing concern for people like those in the high-risk areas in Florida. Okay. Now, one of the things that we can do, increasingly we're using satellite data, and we're using high-resolution radar data that's satellite-borne to measure changes in elevation. Now, this particular example is changes in elevation, and red is about 6 centimeters. Okay? To purple is about 3 centimeters. So we're literally, over this distance, measuring some areas that are sinking almost imperceptibly. But you begin to see that there are distinct pods of subsidence going on over a 35-day period. And these are associated with mining. So here we've got a documentation of where mining in the subsurface is slowly but steadily causing subsidence to occur. Okay. Now, broken water mains, classic. We see this actually in Houston. This is a, quote, sinkhole caused by heavy rains. This is underground pipe that ruptured, severing major highways. Okay. Now here, it's clear that something is controlling the distribution of these sinkholes, and they are in fact the shafts, the underground shafts of coal. And the way that you mine underground coal is you typically leave pillars so that it doesn't collapse on you, at least when you're there. But eventually it tends to collapse, and so the pillars are the areas in between, and then the holes are the areas in between the pillars. Okay. So here we have a fairly typical pattern of collapse associated with coal mines. And this is that room and pillar scheme of mining that tends to give you that strange rectilinear pattern of sinkholes. Okay. Now, at some point, the purpose is to mine out the pillars. And so here is a seam of coal that they've removed the pillars, and now they're beginning to remove out. And what's happening is you're beginning to get a large trough that's collapsing. This is called trough subsidence. Okay, and there's some local subsidence as well, but this is a much larger scale form of subsidence associated with coal mining. So there's a variety of types of mining and a variety of types of subsidence associated with the mining. I'm not going to go into the various types, but in some cases the assumption is, yes, it will collapse. And so literally you're mining in this direction, you're allowing it to collapse behind you, so that the collapse is not a surprise, but rather hopefully intentional. So quite literally, it's not a job I would like, but you've got this system where you're mining coal seam, and there's just this little narrow area here that's supported, and then everything else is collapsing. Okay. This is a proverbial leap of faith. Sit down in here as it's going in this direction. Okay. And so these are just various types of subsidence that you can get from trough, individual sinkholes, etc. Okay. Now, remember I said that we get some dissolution and karst topography from evaporites, and we actually see some of that with salt domes. And so in this particular example, there was an area of solution subsidence associated with this salt dome, and there was some drilling going on. And the problem is the drilling ended up intercepting some of the mines, and the whole area drained. And so it collapsed and drained going into this. And literally this drill ship was just destroyed as they intercepted some kind of a fracture zone or a fault. And so it began to fill in this abandoned salt mine. Now, we actually use these abandoned salt mines to store oil and natural gas, particularly oil. This is part of our reserve program, is filling these pre-existing holes. The problem is we don't always know how they're interconnected because they're highly fractured. This particular sinkhole occurred not far from Texas. It's called the Texas Tar Pit in 69, 81, and 2008. And you can see how it was growing up to 900 feet wide before they finally stabilized it. And the kind of tar shape, or the tar look, is basically the oil that was seeping from within it. So this was actually an area where they had stored oil in the salt dome. So this was within 50 miles of Houston. So this is the type of subsidence that you get with evaporites. This here, this was lead zinc mining and collapse thereof. This one's kind of interesting because it formed from salt, and it formed within about 4 hours. So very quickly, they were extracting the salt. They had this huge sinkhole develop. So these are one of the issues that we have to deal with, both the natural as well as the collapse associated with the extraction of the fluids. Okay. If we look at areas where human-induced subsidence has been major, New Orleans, Houston, Galveston, Mexico City, San Joaquin Valley, California, Las Vegas, Venice. Okay, so we're going to look at these as case studies to see what is it that's causing the subsidence in these areas. Now, in the case of New Orleans, it's kind of controversial in part because there is regional subsidence that's going on in the Gulf Coast, and that is due to salt withdrawal and to a lesser extent sea level rise. And the argument is to how much of one versus the other goes on today. But the other thing is the subsidence, whatever the cause, is causing a huge loss of marshland. So that the yellow is land that's been submerged in the last about a 60-year period, and some erosion, but mainly we're losing land in Louisiana, in coastal Louisiana, because of submergence. And the submergence is some combination of the lowering of the ground and the rise of sea level. And the lowering of the ground is some combination of this regional subsidence that's associated with salt and some other things. This red is areas where we've lost land. Okay, and trying to decide what is the driver is important in part because, well, we're looking for somebody to blame, but also we're looking to see what can we do to stop it. So if the answer is at 5,000 feet or 60,000 feet, the salt is moving, we're not going to stop it. If, on the other hand, it's groundwater withdrawal, then we can stop it. So this is what we're trying to figure out. Yes, ma'am?
Isn't a lot of the erosion because of them not letting the Mississippi River?
Not letting what?
The Mississippi River that flows past?
That would be the, yes, absolutely. And that's something I'll point out in just a moment. But yes, absolutely. Okay. So here is the thickness of Holocene sediment. Very thick at the mouth. Holocene, remember, is the last 10,000 years. And then relatively thick along here. And it turns out that kind of coincides with the area of subsidence. And so that's our first clue that at least one of the drivers is subsidence. Now, in this particular case, it's not just regional subsidence associated with salt, but it's actually subsidence of the underlying clays. The Mississippi River is a clay-rich river, or mud-rich river, but a lot of clay. As the sediment is piled on, as it's deposited loosely, and then it gradually sinks. And so the natural sinking of the land associated with the deposition of thick muds is very common. In fact, one of the ways we can try to keep up is to continually dump more sediment to try to keep up. Now that does two things. It piles up, but it then causes more subsidence. So this is a game of continually trying to fill it up. So how do we do that? By allowing the river to overfill its banks and deposit in the floodplain. As soon as you stop the river from depositing in the floodplain, the subsidence is still going on, but we're no longer piling stuff on top to try to keep up. So a lot of the marshland loss is due to subsidence of the Holocene, but it's aggravated by our building of levees to try to prevent the river from depositing its sediment on the floodplain. This is a problem we see in the Nile River today, Mississippi River, etc. Okay. The other problem is there is a lot of oil and gas withdrawal, and we know that that can cause subsidence. And there's a lot of trenches. Well, trench is not quite the right word. Areas where they've cut through the swamp to allow small boats to come through. And what that does is it tends to drain the swamps. And as we'll show in a second, that causes subsidence as well. So there, when you ask the question, why is the New Orleans sinking? It's a complicated answer. It's sinking for a variety of reasons. Having said that, the net result is the city's below sea level. And so, irrespective of how you got there, you have to deal with how you live with it, and are there things you can do that would minimize the continued subsidence. In Central California, we have a lot of subsidence. In fact, it's one of the first areas that was recognized, and the subsidence is due to three things: groundwater withdrawal, the compaction of peat here, and then hydrocompaction, that's down in here. And that's basically by flooding of waters on top of it. That's not as major, but I want to talk about groundwater withdrawal and peat compaction. Okay, and let's talk about peat compaction first. Notice, if you will, that the area where we have a lot of peat compaction is in the Sacramento Delta. The Sacramento Valley, or rather the Sacramento River, drains much of the Great Valley, and basically it comes out into San Francisco Bay. And there's a large area that's called the Sacramento Delta where a lot of the sediment is deposited. Now, the thing is, here's a couple of distributaries from a delta, and there's a little natural levee. The sides of the distributaries are a little higher, a little coarser, and then as you get farther from the river, you get into muddy and organic rich sediments where there's a lot of peat that's been growing for quite a long period of time. Now, the problem is we would like to build homes here, but nobody wants to build on a marsh, on peat. It's just not dry. One, it's not dry, but two, it's also a little too soft. And so what you do, you drain it. You drain it and you compact it. Okay. Well, that's good. Okay, now we have a dry, drained place that we can build our houses. And that's what we're doing in this area around here. The problem is that when you dry it, you oxidize it, and that actually causes additional subsidence. And so we're getting up to 15 feet. The darkest areas here are subsidence more than 15 feet below sea level. I mean, this makes New Orleans look like a piece of cake. And so what's happening, of course, is people are moving into these newly drained areas that are subsiding. And the comment here is that they're moving on the floodplains, and the only thing protecting the home is an earthen levee that everybody agrees are just kind of falling apart. So we're doubly damned. We have created a space that results in subsidence, and now we're putting people into that space, which, because of subsidence, is more at risk to flooding. And so this is a major problem in this area. You see here, draining of the delta, subsidence, levee instability. There's increased saltwater intrusion. And there's all sorts of problems in terms of reducing surface water, increased reliance on groundwater, which in turn causes more subsidence in these areas. So let's look at this one. This is probably the classic example in the Central Valley of over 20 feet of subsidence. Okay? And that area, right in here, here's where the ground was in 25, 55, 77, and it's continued today. Just imagine that much subsidence having occurred. Okay. Well, the reason for that subsidence is that we're withdrawing water from a zone that's relatively shallow, a few thousand feet, but more importantly, the aquifer from which the water is being drawn is overlain by a thick lake bed. There was a large lake that filled the San Joaquin Valley when that outlet into San Francisco Bay was geologically closed. And so we have very thick, clay-rich sediment that's relatively young. Now, the importance of that is that it's relatively young, and therefore the clay is still more or less as it was deposited, kind of in a house of cards. A lot of porosity, okay? Not much interconnected permeability, but a lot of porosity. As you suck out the water from the aquifer, it causes a gradient that causes the water to be sucked out of the clays, from between the clays, better said, and so the clays compact. And as the clays compact, if it's near surface, then the surface lowers. And so what we have is this surface subsidence due to groundwater withdrawal associated with compaction, of this case lake deposits. And that's the main way that groundwater withdrawal, or for that matter even oil and gas withdrawal, can result in surface subsidence. Okay. In Nevada, we can look at, again, this INSAR data. This shows changes in elevation with time, and we see there are a series of low areas that are bound by faults. And this is just a visualization of it, and what's happening is we're withdrawing groundwater again. So the withdrawal in arid regions is particularly sensitive because we need the water and we don't have enough surface water. So we have major withdrawal, major subsidence rather, and literally in some cases we get these big tension cracks that are forming in the Nevada area associated with these fissure zones that are really the surface expression of old faults. The faults are controlling the geometry of the subsidence bowl. Okay, but literally they're allowing extension and cracks moving all the way to the surface. Okay, and so we can look at how that subsidence has grown with time by looking at time slices of these INSAR surface elevation data. Okay, so it's a good way of visualizing how subsidence is changing both with space and time. Now, our local example here is the Brownwood subdivision. It doesn't seem to be a particularly appealing area to build your house. But when it was built, that was 8 feet above sea level. And at the time, it was a thriving subdivision, but it now is below sea level. And the homes were largely destroyed in the last hurricane, the last few hurricanes. So why is it that the Brownwood subdivision became the Brownwood Marsh and the Brownwood Bird Sanctuary? And the reason is it's sitting in the bullseye of a subsidence bowl. The subsidence bowl that really has its main center around the Houston Ship Channel, and then a secondary bowl right here around Brownwood. Okay. And if we look at that, we see another hole down here. That zone of subsidence, up to about 3 meters, is coincident with the lowering of the water pressure associated with the municipal and commercial wells that are being pumped in this area. This is where the Houston, Galveston area dropped their water from pumping in these areas here. Okay. Now, because of that, there was major economic damage to the ship channel. Brownwood, need to say, was gone. And so in about 1970-something, the region, the Houston-Galveston area region, formed a planning body called the Subsidence District, Houston-Galveston Area Subsidence District. We talked about who determines what you can do with your land. Well, in this case, this is the regional facility that determines where you can get your water. And the reason is because it affects the land. And so they basically said, we're going to shut off pumping. Now, they didn't do it all at once, but basically they said, we're going to shift from groundwater to surface water. And they started in the area that was worse, and then gradually they've been extending out to the north and west, going from groundwater to surface water. Okay. The problem is now we have a new subsidence bowl. It's out near Katy. And the reason is the people are moving faster than the subsidence district can keep up with. So these now are the wells that are pumping water for the areas to the northwest. This is kind of the direction that the enforcement was going, okay, in Harris County, and you can see we just haven't gotten to this area yet, okay. In fact, you've got up to 4 feet in that area since the subsidence district was developed. Notice, though, in that bullseye, a foot or less. So we pretty much shut off the subsidence in the Ship Channel area that affected most of the Houston region. But we still have an area in Katy and in Richmond, Rosenberg, Sugarland that's still reliant on surface water and still causing subsidence. Now, there is an argument that's made, mainly by the people up here, saying that we shouldn't have to go on surface water. Now, the reason that they don't want to go on surface water is the reason I didn't want to go on surface water. It's more expensive. But in doing so, it stopped the submergence. And the subsidence in a coastal region means literally the sea is rising. And they're saying, oh, but we're really quite far away from the bay, and so it's not affecting us. And that actually seems to make a lot of sense until you think about the rivers that are flowing in this direction, okay? So here's that river, and now what we're going to do is we're going to have 4 feet of subsidence. Now there's that river. Now the river does this. Now, what happens to the velocity of that river when you make it steeper? You increase velocity. What happens where you make it flatter? You decrease velocity. What happens is a river is speeding fast and then slows down. Piles up. And so you have increased flooding. So what we're doing is we are creating a situation on this side of the subsidence bowl. We are causing a back tilting of the river and causing it to slow down and flood more. So subsidence is a problem even where you're not at sea level, because you're changing the gradient of the drainage. And whether or not something is eroding or depositing, or rather flooding rather, very much depends on the gradient, ultimately the velocity. Okay. Now let me just show you one example of a case study as to how this might come into play. This is an area that's along the San Jacinto River, and this is a levee. This is a breach in the levee, and this is an anchorage point where barges are temporarily stored. And so the people that owned this were being sued by somebody else saying that they didn't really have proper title to that. And they said that that land in this that they owned should belong to the state, and they wanted to buy it from the state. Well, the other group said, no. In fact, that was land back in 1916. This was that same levee. And that was what we call a crevasse splay. And a crevasse splay is an area where the levee is locally breached, and then you have this slug of sand and sediment, that forms this little delta into the adjacent bay. Okay, and so this is where the land, actually, yeah, this is where the original title came from. Now, the problem is, yes, this was land here in 1930. Okay, and notice there's no breach yet. And you can see the oak trees here. You see this channel here. There's a channel here coming through here. Well, now they've made a cut in 1950. You can still kind of see that channel, but notice it's getting a little disconnected. The area that was very distinct and vegetated here gets fuzzy here. And now it's bare of vegetation in 61. You can still see that channel, but it's just locally emerging. And then finally you see it here. Well, if you look real closely, here's that channel. And if you look at the maps, going back to 1955 and even 1930, you see what's happened. This whole area has become submerged. Okay? Now, you can look at the shorelines over time, and you're really more or less looking at a topographic map of that crevasse split. It's as if the water level was rising. In this case, the land was subsiding, with relatively little change in the shape. Okay? Now, why is that important? Well, this is where the land was in question. And the state and the people that were contesting the owner's land of this said, well, this area was lost due to erosion. And so I, among other people, were called in to say, no, this land was lost due to submergence. And it's part of that large subsidence bowl. And so then they came and said, oh, well, yeah, maybe subsidence was occurring everywhere, but not here. Not here. And it was erosion. I said, well, no, you can still see the natural feature. No, it wasn't erosion. And now, why was it important? Well, it turns out the law differentiates loss of land by erosion versus loss of land by subsidence. And if you're in a river and you lose land due to erosion, you're just up the proverbial creek. It's gone. If you're along a river and you lose the land due to subsidence, particularly human-induced subsidence, you get to keep it. Oh, that's good. Okay. Well, I was convinced that it was very clear it was due to subsidence. Well, then the judge said something funny. It was a trial by judge. Well, since the experts can't agree, and I'm thinking, well, of course we don't agree. That's the whole reason that we've got two different sides. I'm trying to say it's subsidence, and they're saying there's no subsidence due to erosion. He said, let me ask you a different question. Is this a river or is it an estuary? That one caught me by surprise, because my question is, what difference does it make? Huge difference. Because it turns out coastal law applies to estuaries. Coastal law, if it's subsidence or erosion, you lose it. Rats. So then we had to decide, is it an estuary or is it a river? Well, long story short, there's a lot of different ways of defining an estuary, but for the most part, it has to do with tidal influence. Tidal influence along these rivers goes up 100 miles. So by that definition, the whole San Jacinto River, all the way up to Lake Conroe, is an estuary. Makes no sense geologically, but laws are built on funny things. And so we lost that case, and he lost his land because it turned out that it wasn't a river issue, it was a coastal issue. From a scientific point of view, it was a question of subsidence versus erosion. But it's always in a context. So keep in mind the context. I'm not going to go into this except to say Mexico City is sinking like a rock. And why? It was an old lake deposit. Remember that lake that shook so much? Well, take the water out and it sinks so much. So this is a problem that the geologic setting, the local geology, has a lot of implications. And that's it. Give me an email if you want to get together and look at your exam.
Tomorrow, do we still email you? Or
Yeah, just so that I know when you're coming.
Okay, thank you.
No problem. Just